mass of a black hole and the initial velocity of the spaceship that will launch from a planet. So we're initially giving the x and y positions of a star in respect to an unknown object, which is the black hole in the middle, and our mission is to compute the mass of this black hole using the momentum principle and the given positions of the star. And then afterwards, we're going to use this mass to find the initial velocity so that a spaceship on that planet can fly around the black hole without colliding with the planet. And the fundamental principles we're going to use are going to be the universal law of gravitation and Newton's second law for the position and velocity updates. So delving a little bit more into the physics fundamentals, here's the universal law of gravitation. This is, as you can see, the position vector is negative to the force of gravity. We have the Newton's second law decomposed into both the parallel components of Fnet and the perpendicular ones, where the perpendicular one, in this case, due to circular motion, it's the centripetal force, and the parallel component of Fnet is the change in momentum over the change in time. By the way, the vectors are given in bold. And so we have our usual position and velocity updates, given here, the kinematics. For this equation, I'll just highlight. This equation is going to be continuously used using a velocity final for velocity initial, as acceleration is non-constant. And then finally, for this experiment state, we're going to be assuming that Fnet equals to Fg, which is how we can derive this formula for mass, as our Fnet parallel is the change in momentum or the change in time, and as we made Fg Fnet, we can equate these two equations and come up with this equation for mass. And by the way, Fnet is equal to Fg because we're in space, and yeah. So here are the initial conditions. The gravitational constant, the mass of the star, delta t is number of seconds in 1 day, computed as you can see in this way, and the first data observation is going to be taken from time 0, it's seconds. So here's the code for finding the mass. We're using Newton's second law to calculate Fnet, which is here. And so then we break it down into the parallel and the perpendicular components, where the parallel component, as I showed in these previous equations, is the magnitude of P final initial divided by delta t. And of course we have to calculate the vector, which is in the direction of momentum here. And we do the same thing for, the perpendicular component. We essentially take Fnet and we subtract the parallel component to get the perpendicular component of Fnet. So having found the Fnets, we are now able to calculate the mass. And so again, we just take this equation, we compute it, MBH here is the mass of the black hole, and we print it to get the following results. Essentially the results slightly changed throughout the trajectory, but what I did is I took an average of all of them to get 1.6 times 10 to the power of 34 kilograms. Of course, this could cause a potential error, as more data points could have been used, but I went with the scientifically recommended amount, 6 data points, and took the average because otherwise it would have been way too long. So here are our mass. Here's our mass, and now moving on to the second part where we're calculating the initial velocity of a spaceship. We've entered the mass that we just found onto this different variable, bh.m, and we have these other given conditions, then the initial conditions for the speed and the planet velocity. And then we move on to calculating the Fnet on the Fnet on the planet and on the ship. For this, first of all, we're calculating the r hats on the r hat of the black hole on the planet, the r hat of the ship of the planet, and the r hat of the black hole on the ship. So we have 3 different r hats. Well, first of all, 3 different r's, and then we divide them by the magnitude of r to get the 3 different r hats, and then essentially we use 3 different universal gravitation equations to calculate 3 different forces, which is the force of the black hole on the planet, ship on the planet, black hole on the ship, all of these, to then finally calculate the Fnet on the planet, which is the sum of the force of the ship on the planet and the black hole on the planet, as well as the Fnet on the ship in the same manner. So now that we have all these Fnets, we again use the Newton's second laws. Just zoom out a little. Newton's second laws to compute the trajectory of the spaceship and the planet. And of course, there's like an if statement that was given, but this is going to determine if we got sucked into the black hole or if we crashed into the planet. And so the results we got from this are as follows. I did a trial and error for the ship speed and the x and y components, and these values, the negative 4.27 to the power of 10 to the power 7, and this speed for y, seemed to work very well. It did not give me a crash note, and the trajectory seemed pretty reasonable. And now of course there may be potential source of error, as these velocities were guessed and checked, but these initial velocities work pretty well. And so in conclusion, here's the average mass that we calculated, and this is the initial velocity, the velocity initial that I chose. We did this using the universal law of gravitation, calculated the net forces on the celestial bodies, then used the Newton's second law to calculate their trajectories and in orbital motion. Then of course we identified potential source of error, and in the process we learned to interpret code. Now moving on to the what if analysis questions. One of them asked if we were trying to, instead of just not make the spaceship crash, if we could put it into orbit as well, which through trial and error I got this initial velocity that gave me this trajectory, and it did orbit to an extent, except the very, very last part, but I did not know how to fix that. And my reason for choosing this initial velocity was I tried to decrease the x component of initial velocity and increase the y component, so that, but very similarly to the planet, so that they would not crash, but they would present the same trajectorial motion. And now onto the question, what does it mean? It asked how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. And so, just to break it down, what everything means here, F net could be broken down to parallel and perpendicular components, and the parallel component is the change in the magnitude of P over the change in T, whereas the perpendicular component is the centripetal force. Whereas the rate of change of momentum is just momentum final minus momentum initial divided by the change in time. So this is a vector, and here we have the magnitude, and so yeah. But thank you, and see you in 2 weeks.